Hello again. In the second video, part 2, we are now going to look at the question of how far does an object fall when it's in free fall. How far? And again, I'm going to introduce you into a new equation. So we're going to add one more equation onto our list. Okay, I think for this example, we're going to have a simpler situation to start with. And what we're going to do is imagine a person who drops a ball and releases the ball from rest. Okay? So this is just going to be letting something go and letting it drop off of the edge of some building. Okay? And what's going to happen, of course, is that this object is going to accelerate on its way down. And you know from the pivot activity that what will happen if you drew pictures would be something like this. That initially the ball would not travel very far. So if this is position A, then maybe 1 second later the ball doesn't go very far because it hasn't had a chance to speed up. But if you wait, you'll notice that it moves quite a bit further for position C, D, and it keeps on going, right? So the E would even be further. And so the fact that these distances are stretching out is a consequence of acceleration. Now, what we want to do is figure out how far the object is falling. To answer that question, you have to first establish a reference position, a coordinate system. So what we're going to do is make this position right here, y equals 0. And any position underneath that is going to then be negative. So again, anything underneath is going to be a negative y because you're going down on your coordinate system. So we have to kind of stick with that as we do this example. We have to commit to that. Okay. So let's make a table again. And again, we're going to do 3 columns. The first column is going to keep track of our location. And how about we go all the way to position E? I know I didn't show that on my drawing because I ran out of space, but we'll just go up to E. We are going to keep track of the variable time, t. We're going to use units of seconds. And then we will keep track of the position, which has the variable y. The units are meters. And of course, we'll say we like this at 0 seconds you release something, and then 1, 2, 3, 4. So we're going to pick equal time intervals like that. Now, the question is, at this point, how do you determine this distance? The only position that we know for sure is the beginning, because we know that when the ball is released at A, it's at the origin, so that's 0. So the question is how do we get these other values? We know they should be negative because they are all below the origin. And we know they should be getting bigger because of common sense. So what I'm going to give you at this point is I'm just going to state a formula, and we're going to use that. And the formula goes like this. The formula is that the vertical position is equal to 1/2 times the acceleration of the ball times time squared. And I am not going to derive this. I'm just going to say that it's going to make sense. And you'll see when we start getting numbers that it gives reasonable numbers. And if you're interested, we can talk about where it comes from. But for now, that's beyond the scope of our lesson. So let's use for the acceleration -10. Why negative? Because gravity has a downward acceleration. And like before, we have to keep track of that and use a negative sign. Should I use 9.8? Well, not right now. Okay? If you're calculating more precisely on your own, you should use 9.8. But I think for now, we can just talk about 10, and that gives us a good idea of what's going to happen. So what does this formula break down to then? You've got 1/2 times -10, which is -5, times t squared, which is the variable. And so what we need to evaluate is only -5 times t squared for each of these times. And that should tell us a position. So let's try it out. So -5 times 1 squared, right? T is equal to 1. -5 times 1 squared is -5. So the ball falls 5 meters below the release point in 1 second. Sometimes students are bothered by this, and they think it should fall further. Okay? But actually 5 meters makes sense, because when the ball is released, its speed is 0. 1 second later, its speed is -10. So its average speed is actually the average of 0 and -10. The average speed is -5. And if something moves with an average speed of -5 for 1 second, it's going to travel -5 meters of displacement. So if you were wondering, that's why that makes sense. Now, you can figure out the other values for yourself. 2 squared is 4. 4 times 5 is -20. 3 squared is 9. 9 times -5 is -45. And 4 squared is 16. And 16 times -5 is -80. So the results that we get here actually show that the position is growing, not in a direct proportional way, but in a growing way. And it's stretching. It only falls 5 meters here, but then it falls 15 additional, and then 25 additional, and then 35 additional. Okay? And that pattern is actually the pattern that corresponds to a mathematical shape that you know about. And if I make a graph of position versus time, I'd have positive positions up here in the first quadrant, negative positions here. And if I graph these values, I'm starting at 0, and then I'm going negative, and I get that sort of a shape. And folks, that is the parabola. That is a downward-facing parabola, or half of one, if you like. And that shouldn't surprise you, because in math class, you probably would recognize right away that you're graphing y is equal to negative some constant and times x squared in math. But this isn't math, this is physics. So we say y is equal to -5t squared. Okay. So this is how you find the displacement of an object when you drop it from rest in a gravitational field or a field that has a constant acceleration. Okay. Now, there is one more term that gets added to this, and I don't think I'm going to go through this example with you because you're going to do some practice on your own to discover this. But the full formula for determining the displacement of an object, or I should say its final position, is going to be this. And this formula looks exactly like the one we just talked about, with one difference. And that difference is you have an extra term here. And that extra term basically takes care of what happens if the object has some initial velocity to begin with. So for example, if the person throws the ball down with an initial velocity of 30 meters per second, and then I made a mistake here because it's not positive, right? If we do that, it's -30. And the way that you would handle that is now the ball's going to go that much further as time goes by. So let me just give you an example. So at the beginning, at t is equal to 0, y would be equal to -30 times 0 plus 1/2 times -10 times 0 squared. And of course, that's just 0 plus 0 because the object is at its starting point. Well, things get interesting when time goes by. So for 1 second, you would take, again, negative 30, but now you're multiplying it by 1. And then you add plus 1/2 times negative 10 times 1 squared. And so what you get here is negative 30 minus 5. Of course, that's negative 35 meters. Remember when we did this example before? Remember that was only 5 meters before, right? After 1 second, the ball only traveled 5 meters in the first example. But now we've given it a very fast downwards velocity, and so we have to add this term on. And so that's how this works. And so you could continue, and you're always going to be adding on, some term here. Just remember to increase the time to 2 seconds, to 3 seconds, etc. Okay? So that's how we use that formula. If the ball was thrown upwards, then you wouldn't write negative 30, you would write positive 30, and you'd get very different answers. And I'm going to let you discover some of that through the problem solving.